Our next presenter represent company is a startup called Next Move. And that's even name of this company already attracts attention of our community because decision management is frequently about finding optimal next move. Whatever decision we make, maybe it's a chess problem, or maybe it's just assigning, for example, selecting next track from previous problem when Helmut described, or a lot of other problems always deal with next best action, right? That's how it's called in our community. And the name Next Move really attracts attention. And but it's not Ryan and Nicole, the founders of this company, but they concentrate mainly on certain optimization areas, and in particular, their main interest, if as far as I know, it's a real-time routing and delivery problems. And they will tell you more about this, and they want to share more testing optimization model, how it works in real production environments, and it certainly is related to what we usually do in decision management. Ryan, Nicole, please present yourself, and we're looking forward to your presentation.
Yeah, thank you, Jacob, for that wonderful introduction, and also thank you for organizing DecisionCAMP. This has been a really cool lineup of talks, and we're happy to be part of it. You're correct about the name of the company, and as an addition to that, the MV is based on the Unix command move. So when we founded it, we were initially thinking about, it's sort of like Unix components applied to decision making. So that's just a small historical note which might be of interest. So I'm excited to talk to you all to all of you today about testing and decision models. This talk will be a bit about models, a bit about operations, with a heavy skew toward real-time delivery operations, because that's where we've spent a lot of our time, but it also applies to a lot of other things, and a bit about software. I will first apologize because I come from an optimization background. I will try to use the term decision model wherever I meet here, but sometimes I might slip into the term optimization model. If I do slip, for our purposes today, these are equivalent. We're thinking about them the same way. We do use a lot of optimization, but we're thinking about decisions.
Yeah, decision optimization part of decision modeling. It's not very popular, and not everybody in our audience familiar with different heuristics. So, like you mentioned previously, Bender's decomposition. So, but if you stick to more business application, it would be useful.
All right. So, quick intros. I'm Ryan, the CTO and co-founder of NextMove. My background is in operations research, and I spend a lot of time in real-time delivery. Nicole is our VP of engineering. My other co-founder actually was Carolyn Mooney, who's not with us here today. Nicole comes from a statistics background. We worked together a lot in on-demand delivery and gig economy operations for the last several years. And at NextMove, we do everything from parcel delivery to restaurant delivery to shift scheduling and carrier selection, again, with a bias towards on-demand operations. These are environments where decisions like routing frequently have to happen in real time. And depending on the kind of problem, this may mean sub-second optimizations. It may mean you only have a number of milliseconds to make a decision. Or you might have an hour overnight. It just kind of depends on the type of operations that you're doing. Delivering groceries is different from delivering food, which can get cold quickly, which is different from delivering parcels. These operating environments are also changing fairly frequently. Many of the companies that do these things have been in expansion mode because they're experimenting with new business models. Technology-wise, they pretty much all use agile processes, and they do continuous releases to adapt their software stacks to their business needs as those businesses are changing. So that's been kind of unique about this field, is that a lot of the players in it have been growing and moving into new territories rapidly, and that means just a lot of drift in the problems that they're working on. So what we've found doing this is that effective testing in these environments is one of the hardest things that we've had to figure out, partly because there aren't really standard patterns that you can just take off the shelf and plug into your operations. So at DecisionCAMP, we've been hearing a lot about strategy and policy decision making. This talk has a little bit of a different flavor. We're going to be talking about testing decision models in operational environments such as on-demand delivery. We're not going to be presenting any new types of testing. What we have done instead is organized a workflow of testing based on what we have applied and what we've seen our users applying in these types of environments. And figured out how to combine that with software engineering best practices into a flow that works in these kinds of organizations. So the question here is not what new types of testing we can develop, but how do we organize different testing for decision models to work alongside software development operations? So we'll start with a couple stories from our experiences in the field to motivate different kinds of testing. Then we'll dive into these different types and how they play together into a software engineering workflow. All right, so first we'll do some stories. Again, Nicole and I have been working together in on-demand logistics for a number of years. We'll have a couple stories from our experiences in the field to set the stage for why this is important and how it can impact production environments. So for our first story is a tale of tacos and fried chicken. This comes from the field in a large gig economy restaurant delivery service, where there was essentially a collision between business strategy and real-time operations. What happened here was that the business development team partnered with a large fast food chain. That's why we've put all these Taco Bells on a map, just to give you a sense of what this looks like in real space. And there wasn't really a convenient way to project how this partnership would impact KPIs. So the organization couldn't answer questions like, should they have a dedicated driver pool to doing these fast food deliveries? Should they subsidize tips or increase delivery fees to make drivers more willing to go to these fast food restaurants and actually make these deliveries? This was a gig economy model, so you can't exactly tell a driver where to go. You're essentially making offers and acting as a marketplace and hoping that somebody will actually pick up an order and take it somewhere. So instead, we ended up doing what most people in our position do. We crossed our fingers and hoped that the decision algorithms would do the right thing. And that sounds ridiculous, but it's not entirely unreasonable because it's essentially what we do every day. These businesses are changing all the time. We have to sort of deal with drift. And so, we have models that do make these decisions, and it's not unreasonable for us to think that they will continue to perform those same functions as that environment changes. The question really is is the environment changing so much in this under these new conditions that the model should have been adapted? So in a delivery marketplace, topology of a region is really important. Where is your demand? You tend to have clusters of people that live in certain areas, and you tend to have clusters of restaurants that are actually in different areas based on zoning laws. And again, in gig economy models, no one actually has to do anything. And the way it often works is that high value orders have a much likelier probability of being accepted by drivers. And pairing orders together can make your regions more efficient because you're essentially changing the unit economics of a given route. You're making it more valuable to a driver. And the enemy of delivery, especially on-demand delivery, is really low-value orders that are far away from each other. And that's exactly what you end up with in this kind of situation. I think if you look at a map of Indianapolis, for example, it has something like 100 Taco Bells, and they're all dispersed around the city center where none of the other restaurants are. So because we didn't have testing to understand the impact of this partnership in advance, we weren't really able to be proactive about system performance, and it did have some pretty big changes.
I also have a story to share. At one point, our dispatch system was based on an open source solution, and we weren't sure of the limits at scale on larger order volume. And one Friday night in a big city during dinner rush, we found those limits. We'd hit this unsupported order volume, and the algorithm just fell over, and no plans were output. And every minute that passed, the problem was exacerbated because those unplanned orders just kept piling up and coming to the next plan cycle. And so we ended up having an outage for a couple of hours, and there was a pretty negative customer impact, and we lost some revenue as a result of that. So what could have stopped this from happening? What would have helped us? A couple of things. One, scenario planning or scenario testing for volume limits. If we would have had the tools to be able to run some tests at higher volumes with synthetic data or forecasted data as a result of the partnership, maybe we would have been able to predict that the algorithm would have fallen over at that load. Another thing that would have helped us is shadow testing or shadow modeling with a backup algorithm that basically just ran a simple model that delivered results. And if our main algorithm would have fallen over, we could have activated that shadow model and actually saved ourselves from an outage.
So we've established that testing would have helped us in our past lives. So, why didn't we do these things? And it's a valid question. And a lot of companies that should be doing this are not. Why do we rely on running production operations and looking at outcomes post hoc? And part of this is a methodology question and an infrastructure question. And part of it is, that we don't really have a standard, sort of workflow and set of tools to plug into infrastructure that work well on decision or optimization models. So let's take a step up from here and talk about what decision model testing is. So when we're testing, what we're essentially trying to do is two things that are the same sides of the same coin. One is we're trying to reduce risk in making a change to a model and rolling a model out into a production environment and actually sort of activating it. We want to know that doing that is not going to have some sort of negative impact to KPIs, that it's going to actually be making decisions in that environment. And the other thing we want to do is increase confidence within our organization. And that really amounts to stakeholder buy-in. So testing does both of those things, or it can. And you can operate a business without this, but as you've heard from our stories, risks abound. One of the issues here is that operational environments change in small ways over time, and those changes accumulate. This is known as drift. And at some point someday you'll come to a point, if you're experiencing drift, where the model just doesn't work anymore. And it's actually very difficult to know when that point is. Now, testing is not new to software, and models are software. Everyone probably remembers some number of years ago when we all started unit testing software and doing integration testing. And now a lot of that has sort of been baked into standard processes. Optimization in particular is kind of a special snowflake in that it's not really straightforward how to test an optimization model. There isn't really an equivalent of a unit test to something like a mixed integer program. Now, this may not apply quite as much to something like a decision rule, but depending on the kind of technology that you're using, like the constraints may overlap in weird ways that make it very hard to reason about what are the set of feasible solutions, which is sort of the same problem that optimization has in general. How do we know that the output of a model is optimal without sort of just trusting the solver to do the right thing? Building decision models is unique also in that it impacts lots of stakeholders across an organization. So if you're at a company building decision models, you likely have stakeholders in the product organization and your logistics arm and your technology arm, like SREs, want to make sure that your models aren't just going to fall over. And your finance division, because the models that you're building have some sort of P&L impact to the company. All of these stakeholders have sort of a different view with different goals into what you're doing, because the algorithm affects all those parts of the company. Testing is, so beyond sort of readiness and production readiness of a model, testing is a way to give visibility across all of these domains into what the model is going to do. Thinking back to Nicole's story, small errors in that instance kept piling up due to one particular failure. So model failures can be very expensive. An error might bring down your system for an entire day or a week, like we saw with Southwest Airlines recently. In real-time operations, one failure can lead to another failure, so they can have these sort of ripple effects. Or in like a big one-off rollout, a bad model that isn't properly tested can be completely catastrophic. There was an article recently about bus routes in Louisville, Kentucky, where students were left stranded during the first week of school when a new routing provider launched.
So we can see now that testing decision models matters, but why is it so hard? First off, technical setup and maintenance. There aren't many out-of-the-box tools that make this kind of testing easy to integrate into your workflows. There are tools like packages and code that you can import into your code base and stand up yourself like Diffie, for example, is one of those. We've also seen some more streamlined offerings like AWS SageMaker, but that isn't necessarily hooked up to the same workflows where you're building your models and your apps. And CI/CD, or continuous integration and deployment, and workflow integration are very important and powerful for de-risking your decision model dev process. But this isn't always done because decision modelers have limited time, and they need to be spending that time on modeling and improving the business and not on sort of standing up infrastructure to do testing in an integrated way. Another reason this is hard is complexity of analysis. Different kinds of tests require different forms of analysis. Maybe you have to do a hypothesis test or a mixed effects regression model to get the results out of your test. Buy-in and alignment also is challenging. Ryan had mentioned that there are stakeholders from different parts of the org, and the stakeholders need to know what they're looking at and what the conclusion is. And if you don't have consistent results and a repeatable presentation over time, they're spending their time trying to interpret what you've given them, and they don't necessarily understand the bottom line. And then the last thing here is problem drift. So what worked 4 years ago might not work anymore. For example, there may have been operational changes that cause you to change the way you pay your drivers. They have a new driver payment model, or maybe a pandemic hit and everything blew up and changed, and your tests that worked 4 years ago don't work anymore. So yeah, that makes it hard. There's another reason testing is hard. This quote comes from the Principles of Chaos Engineering. Chaos strongly prefers to experiment directly on production traffic. Testing on production traffic is basically the holy grail of testing, but it's not where you go to start right away. There is a cost to testing on production traffic, and it's hard to pull that kind of testing right into the front lines. Ryan and I have worked at some pretty mature orgs in the past, and getting testing on production data is very hard to do. So how do we get there? Let's look at a framework.
So we know what decision model testing is and a little bit about why it's hard. Now let's talk about a framework for how to think about decision model testing and how to fit it into our operations and our technology stacks. So these are some common types of decision model testing that we've come across in the field, just organized into categories. First, I'll mention what's not on here. Decision models are usually software components, which means they can be unit tested, integration tested, and so forth. We've just left that off of here because that's sort of implied by the fact that they're software. We're more interested today in testing, which may be specific to decision models. And these are some of the common types that we've seen. So we can batch tests by stages in the model development workflow. For example, batch experimentation is sort of an early on exploratory test. I think of this kind of like exploratory data analysis as applied to modeling. I'm trying to figure out what sort of structure might work for a given problem that I've been presented with. Does this scheduling problem work well with constraint programming or mixed integer programming, or should I be applying a heuristic? What are the impacts of these different constraints in the model? Should they be soft constraints or hard constraints? And I'm just sort of running a lot of stuff and testing the waters and seeing what it comes back with. At some point, we'll build a model and put it into a production environment, and that will be like essentially our first baseline model. And we'll want to adjust that over time as our business changes, or as we see errors or complaints from the field or something like that. At this point, we're going to move into this sort of pre-prod testing, and acceptance testing would be one of these kinds of tests. We can think of this as similar to pull request reviews in GitHub. I'm seeking to merge a change into my production environment, and I want a test, some sort of formal verification that I should expect it not to break things. And by break things, I mean things like both the software and the KPIs of the business. There are also real-time tests like shadow tests, which sit next to production. So we can sort of slice and dice tests by whether they're, where they are in the process or where they are in the infrastructure. We can group them by type of input data. For instance, some of these run purely on historical or in-sample data. This is data that we've collected before, that we've seen in production before. And there could also be production data, which is kind of out of sample data in a way, because all of the theoretically, all of the instances that we'll be seeing in real time are instances that we haven't seen before. And so, if our volume, for instance, is increasing, then I should expect my production data to be of higher dimensions than previous observed historical data. So let's look at production tests and historical tests. What are the system components we need in order to do these things? The differentiator here is that the type of data you're testing on and potentially the environment of the test. These tests are for models in production environments. So it's important that we test them where they live. We can't test them on our machines. They will be living in a cloud environment. They will be running maybe in a serverless infrastructure where we're constrained to like 6 virtual CPUs and some number of gigabits of memory. And that is very different from what I've got on my laptop. The layer at the bottom is foundational components required to stand up robust, repeatable testing. These are things like input sets, which can be pulled from historical data or generated synthetically. Or sort of observability, which is the ability to pull information about model runs out of that infrastructure very easily. And these pieces create an ecosystem where we can slot tests into seamlessly as we develop and adapt our models. This is important because we need to test in a production and staging environment again, not in our computers.
So Ryan just presented the different components that need to exist in order to build out the testing integration flow. And now we're going to talk about how those components all fit together. So this diagram here probably looks familiar to anyone who's worked with Git to version control their software, their decision models. For example, it shows the process of someone branching off of a developed branch and working on a feature and how that makes its way into released software. So Git flow was actually our inspiration for building out our testing integrations at different stages of the decision making, the decision modeling process in order to reduce risk. Now let's look at this workflow. So our goal here is to reduce risk by introducing different kinds of tests at particular points in the development and deployment process for a decision model. So if you're familiar with continuous integration and deployment or delivery, I forget what the D stands for, that's what this is for decision models. So for example, you can see the bottom stream there is the model code path. And what this is showing is that a developer is branching off from their baseline branch. They're working on a feature for a candidate model, and then they're making commits on that feature branch. And each time they're making a commit or making a change on that feature branch, they can be running a batch experiment. And a batch experiment is sort of an ad hoc way of testing or experimenting where you have a set of input files and you're just trying to understand what those changes did to the results of those input files. So that's a really good way to test your changes and understand that everything's working the way that you expect. And maybe you run a couple batch experiments, you see that something looks unexpected, you're getting a higher error rate or something, then you go back and you make more changes, and then all of a sudden you're ready to put up a PR and merge those changes back into your baseline model. And when you put up that PR, that's this this arrow pointing back up to the baseline arrow, which is showing that you're running an acceptance test, and there's this actual criteria of I can merge this PR or I can't. And once you do that, then you're done with your code changes. Your code is merged back in to your stable branch or whatever you're working off of. But now you need to get those changes out into your operational environment. And you can do that by pushing it up to your modeling API layer and running some further experiments there. And so the first experiment that we advocate for running is a shadow test. So what you're doing here is you're pushing up your feature branch and you're running it in shadow mode side by side with your production model, except that shadow model is not making any decisions. It's just running on production data. You're getting the results stored somewhere, but the only model that's making decisions and actually sending results to your operational environment is that production model. And so that gives you an understanding of how your model is performing out in the wild on out of sample data without jeopardizing your production environment in case something goes wrong. And once that test completes and you feel good about that test, then you can move on to the next step, which is switchback testing. And switchback testing is essentially, we think about it like A/B testing for models. It's not A/B testing, but it's like A/B testing in the sense that you're trying to mitigate the risk of network effects, which you have when you are doing, for example, routing. You can't apply a different treatment to individual vehicles because it's a shared network, and the treatment of one impacts the treatment of another. And you can't do it to stops because of the same reason, because vehicles are a shared resource in that network. So we switch back and forth in time, and the units of treatment are actually time units, whether it's 30 minutes or 60 minutes or so on, and you randomly assign treatment or control to that time frame, and then you get what looks very similar to A/B test results coming out of that. And once that test completes, you feel pretty good that you've actually made real world decisions on your candidate model. So now you can push that live into your operational environment and make all of your decisions on it. This is an example of what integration testing looks like, rather integrated testing looks like in practice. This is something that we do at my company at NextMove, and it's part of our internal development process. So every time a developer makes a change to our code base, they'll open up a pull request, and then we automatically kick off an experiment that tests the impact of that change on our solutions. So the results come back, they're communicated to us, and we're all aligned on what's being merged to our stable branch. And if our tests reveal more than a 2% degradation, then we have a Slackbot notification that pings our dev channel, and our on-call dev has to investigate what happened in that code to introduce that degradation. So now that we know how testing can fit into your decision modeling framework, we can take a deeper dive into each of the testing types that Ryan and I have talked about. So this one is batch experiments. This is what I had mentioned in the workflow as sort of the ad hoc exploratory kind of experiment, similar to like, EDA, right? Where you're making some changes to your model and you want to understand the impact of those changes on a set of historical input files. This is the first place that we recommend starting when you're making changes to your model. And it's actually a really nice test to make sure that all of your constraints and objectives are working properly, because testing individual components in a complex model, like a routing model, for example, is challenging. So now acceptance testing is the second test that I mentioned. And you can see the confidence stars bumps up from 2 to 3 here when you're running an acceptance test, because this is a more targeted kind of test where you actually have acceptance criteria that you're evaluating, and there's a go, no-go decision as a result of this. So for example, your acceptance criteria could be my objective value or my number of utilized vehicles should only decrease with this code change. And if either of those do not decrease, then you get a big red X and your pull request is blocked from being merged because that's a violation. A bunch of green check marks means you're okay to merge it, and you could feel pretty confident about moving to the next test.
Nicole, how do you define this acceptance criteria? Is it hard-coded, or is this some graphical interface here? Can you show us?
Oh, what we have, the screenshot right there, that's something that we, that's actually a tool that we have built out at NextMove. So what this is a console, and you actually can put in any custom statistics about your model that you care about. So basically the developer of the model will write in to their model the custom statistics and KPIs that their company cares about. And then they can use our console to define an acceptance test where they reference those custom statistics.
Yeah, probably these acceptance criteria could be nicely presented in business rules, right? That's when you can use a combination of your optimization module that produces results and rule engine as it validates the results that it fits certain criteria, right?
Yeah, definitely. Yep. So one more test that's similar to the previous tests I've mentioned in that it's on historical data, but it's a little bit different in that the intent behind it is different. So scenario testing is good for identifying outcomes for a range of hypothetical scenarios. So for example, this would have been really helpful in Ryan's story from the beginning of the call to help quantify the impact of partnering with a bunch of fast food restaurants. So you could generate some forecasted data to understand, based on where those Taco Bells are located, we could have probably generated some forecasted data there to understand where demand is going to be coming from. And then we could have run some scenario tests to bound the problem, like a low, medium, high volume coming from those restaurant locations. And then we would have understood kind of the lower bound on our KPIs and the upper bound impact on our KPIs. A slightly different use case for scenario testing is maybe you want to tune your model parameters. So instead of varying the demand on the input, you have maybe the same inputs in each of your scenario test files, but you might want to vary the model parameters like the penalties in your objective function. And you can think of this almost like a grid search on tuning your model parameters to try to find the right mix that that represents the impact on the KPIs that you're looking for.
So let's move up a little bit more slowly on the confidence level. Benchmarking is sort of similar to batch testing. I expect we're all very familiar with this. Under the hood, it's really just a way of organizing batch tests and examining their results. These are often run on historical data, which has been collected, or sometimes synthetic data. Things like TSPlib or MIPLib are examples of benchmark sets. In this case, we're trying to compare scale, speed, and performance of models and solvers. So for example, I might have two completely different formulations in a mixed integer programming model, or for two different models, which represent the same search space, but differently. And I want to see which one is better. Maybe one gets to feasibility faster and one has a tighter relaxation and gives me better bounds. Or I might want to compare different search technologies like constraint programming versus decision diagrams. And so this is when I would use that. Now we move into the sort of real-time part of this, which starts with shadow testing. So this type of testing is done live. At this point, we've already done an acceptance test and we've merged code. And now we're deploying a new candidate model beside our baseline model, and they're both running in production, but only one is used for actual decision making. The other, we're just recording the results for analysis. So this runs under production conditions online using out-of-sample data. And it also tests the stability of a new model as a software process. If that new model breaks, crashes, does anything bad, it's good to know that, and I'm not going to be affected in my production infrastructure. I can apply the same criteria to this that I can do to an acceptance test. But the decision point here is not should I merge my code, but rather should I make a configuration change to turn this on in production. And it's also important to note that both this and acceptance testing are run on the model output, not on observed KPIs. So that's a critical note here as well. And that finally brings us to switchback testing, which is the final one that Nicole mentioned. And you can see we've moved all the way up on our confidence meter here. And this may be one that some people aren't familiar with. I believe it was originally developed for evaluating feed for dairy cattle, but I would have to look that up. Again, you can think of this as A/B testing for decision models. It's not quite the same. And the reason is that we have to do special kind of statistical testing due to the network effects in decision models. So let's think about, for example, a routing model. From one request to the next, these might happen, say, every minute or every 30 seconds. The impacts of the decisions that my model makes will propagate through the system for a period of time. So if I'm doing meal delivery, that might be 30 to 45 minutes. If I'm doing grocery delivery, that could be 6 hours or a couple days. And if I switch the model that I'm using in that time frame, there's no way for me to separate out the impacts of those different decisions. And at the end of the day, what I want to be able to do is say, these time frames were mostly impacted by the baseline model, and this other time frame was mostly impacted by the candidate model. And I want to be able to compare those. The other thing that makes this a little challenging is in a lot of operational environments, the demand distributions are non-stationary, as well as many other distributions. So, for example, delivery volume for meals tends to be pretty low at 3 in the morning, but it tends to be really high around lunchtime and dinner time. You also get different kinds of things delivered. Tacos and wings tend to be delivered more at late night. Deli orders tend to be delivered more in the morning. So yeah, again, these are live tests. We've already done the shadow testing. We've already done the acceptance testing. And what we're getting out of this now is a statistical analysis on real production data, on actual observed KPIs, telling me whether or not a candidate model is better or worse from a baseline. So we presented a lot of information today. This was all based on how we've seen testing techniques applied in the field by our users and how we've applied them ourselves, and the ways that we've worked these into our software engineering workflows. We're also interested in hearing how some of you are doing this and whether these things work. So if you want, please reach out. This is our day job, and our website is nextmv.io if you want to find our contact information there. So now we can open it up now for questions.
Yes, thank you very much. It's a really complex application and real world applications. So you guys in the real production for a while?
At NextMove, yeah, for a few years now. And before that, we were working in on-demand delivery at various organizations.
I see. That's why testing is so important, and this is not testing of something static. It's like real-time testing. It's so many challenges. So probably people have several similar experience and can ask interesting questions.
I see Helmut has so many questions.
Yeah. Okay. Questions? Helmut.
Right. Very nice. This is an area that doesn't receive a lot of attention, I think, in the optimization area at least, and it is really, really important. I think a really fundamental question is how do you know if a particular solution is acceptable to the different stakeholders, and how do you actually make sure that you check that if you do a shadow testing, you still have to apply some form of a check afterwards to see whether, it's not just the KPIs that are good, but the solution itself is acceptable. And how would you actually do something like that?
Yeah, I'll give my quick answer, and then Nicole will give a longer answer. So she worked a lot more on some of these sort of long-term testing technologies that we've used at various places. But one of the things that we have done, and I think this is actually a very good practice, is to make the output of the model be expectations. And so an example of that is if I'm routing, the output of the model should not only be the order of the stops and who things are assigned to, but the expectations around when different events will occur. So that we think of this as operational output. So we have had instances where we pretty much always do that, but then we'll have another model which is does things like timing estimation. And so what we're giving out from that model is this operational output, which you can at least get a sense of, how will this play out in the real world? But there's also the question of, are these timing estimates valid or not, which is a separate model that you have to think about. But yeah, that's how I think about it.
So I guess my answer would be that we start so when we're working with decision modelers on their decision models, we'll start out that exercise by asking them what a good result is. And often we'll start by them giving us the results that they currently have. And usually their answer is, we just want something better than what we have now. So we have sort of a benchmark that we can compare against. We also have put a lot of effort into creating more of a workspace for the different stakeholders to come together and understand the impact of the changes. So the main decision modeler who's building out the model can then they have their understanding of KPIs. Maybe they're wrong, but they're using those KPIs when they're running their batch experiments probably, and they feel pretty good that they can open up a PR and have that reviewed. The acceptance criteria is probably defined by the product or ops team, and that's more of a the go or no go, right? Where they've defined the criteria that is acceptable to them. And I think part of what we really focus on is having all of these different decision points throughout the whole workflow, so that if someone got a KPI wrong, it'll come up later, right? Like when they're doing a shadow test, they'll have another opportunity to test things out, and maybe they say, oh, we didn't even think about this as having an impact here, but it did. So at least now we've kind of slowly rolled out this model in a safe way where we didn't make any mistakes running it in production and using it everywhere.
Okay. More questions, please? Sebastian, go ahead.
So, can you hear me?
Yes.
Oh, yeah. Okay. I hope this microphone is okay. Can you give us an example of, if you would have done that shadow test of that example that you were describing in the beginning, what would have happened in a successful sort of scenario?
Yeah. So I'm not sure if I'm entirely. I think I'm interpreting the question right. So I'll give a quick example where we saw a different problem. So this was at an earlier meal delivery provider where we were experiencing volume growth issues to the point where during peak hours the planning was no longer really scaling to the demand. So we would have timeouts. We had 25-second timeouts on our model executions, and so we planned every 30 seconds. And we actually, as a funny note, we ended up going to the Association for Constraint Programming summer school in 2016, and that was our first exposure to constraint programming and decision diagrams, which we were very thankful for. So we rebuilt the routing part of the model using G-code. And all the testing had gone really, really well. We'd collected a bunch of historical examples. The output looked great. It was really stable, really fast. And we were using G-code 4, and we switched it on in production. I think it was on Labor Day. And there was some bug in one of the G-code constraints where it made it spin forever. And so we just had to back the model out of production, redeploy. And so this was part of the problem, is we have this sort of outage while we're redeploying. There's no, and because the model was controlled by a code change, and therefore a pull request, we're merging into a main branch and then pushing that into production. We have this time where we're just waiting for things to happen, and software builds can sometimes be pretty expensive. If we had been shadow testing, that would have just been a simple config change. Like we would have actually just put the model into production, ran it for several days, said, you know what, it's looking good, it's stable, it's producing output, so on and so forth, examined it and then turned it on. In this case, it took about an hour for it to fail, and then we had to take a remediation action.
Sebastian, you satisfied? You want to ask more? Okay, more questions, please. David? Okay, while people thinking, I want to ask a question. You mentioned that you have historical data and you use it for testing purposes. But if you have this data, can you use it for self-learning? From self-learning perspective, can you improve your new decisions using previously made decisions?
Yes. Nicole, do you want to take this one?
Yeah, if I'm understanding the question, I think that's typically how we do it, where you almost you rerun old decisions, the old inputs through a new model. You can also do, actually, now that I'm answering your question, I think I know the intent behind it. Is are you saying basically use that almost like a warm start?
No, I'm more talking about all previous discussion when we use machine learning algorithm to learn from historical data, and self-learning, it's when you're learning from your own mistakes or your own successes.
Yeah. So one thing that we often do is we'll have someone pass in their previous solutions. And basically, we just spit out the KPIs that they were having with those previous solutions. And then it actually showed, because often they don't know that there was a problem until they can see how much better it could be. And at least having like the KPIs presented with the previous solution in the same sort of consistent way as the current solution allows you to learn from what you had before and understand what the pitfalls were. Often someone will say, we have these 7 constraints, like drivers can't drive more than 8 hours a day. These were the time windows that needed to be hit for these stops to be serviced and so on. And then we'll read their previous solutions through and identify, well, your previous solutions weren't even doing that. Your previous solutions weren't feasible. So we'll often be able to, when we compare side by side, we can say either your previous solutions weren't following those constraints or they were maybe worse than what it could be.
Yeah, and I think one of the aspects of this that you're probably asking about is like, could we use, say, reinforcement learning or something to sort of like they do with AlphaGo? I think you could, and that's something at various places that we have considered. A lot of the time, companies that are doing this are moving from manual operations to automation, and so the things that there's one challenge there, which is what you would be learning on could potentially be human. It's neural networks, right? And it may not be as good as your optimization would produce. In order to do sort of self-learning without the human in the loop, you'd have to have a simulation or something that would then have to be have some level of fidelity, and it's extremely hard with the amount of randomness in these environments to get something that is within a reasonable accuracy. Another issue here is that a lot of the time these environments are changing so rapidly that a given strategy, like the strategies have to be really, really general. I'll give one example, which was we were operating in New Brunswick, which is either in Philadelphia, Pennsylvania or New Jersey. I can't remember off the top of my head.
New Jersey.
New Jersey. And it was, the region was fairly mature. It hadn't really changed much. And so we operationally knew what typical KPIs would be. We knew like how long it would take to deliver an order. We knew how many drivers we would need. We knew like what our unit economics would typically be coming out of it. And then one day we turned on a sushi restaurant and it just completely changed everything. Just having this one sushi restaurant that didn't care about hot food sort of over in the corner of the region meant that all of a sudden our KPIs just completely changed. And it took a while for us to figure out like that was the thing that was causing problems in the region. So that was just, you can have these sort of one-off impacts that have a fairly significant effect. But then, for instance, during the early days of COVID, I've heard about grocery delivery companies that had their volume grow by 20% day over day. So when these sorts of things are happening, what good is your old data?
Okay. Okay, we have time for one more question.
I would have a question.
Go ahead.
Okay, I think the most challenging situation, and this is what you experience in your delivery problems, is when you run an optimization model and the solution affects basically what the next run of the optimization model is doing. You may have something which produces very good results for this particular run, but creates a very tough new subproblem afterwards. And I didn't quite understand how your testing approach by running these things alternatively deals with this in a systematic way or in a guaranteed way of detecting this type of problem.
Yeah, nothing is guaranteed for sure. So, but I think up until in our framework that we talked about, up through shadow testing, it is file by file comparisons of KPIs, right? So you're looking at the impact on a single input file and how that compares between the two models. And then when you get to the switchback testing, that's when you actually start to have some of those network effects built in. And so I think the way Ryan was describing it is, you can have variable time windows based on the kind of problem that you're solving. And if you run a switchback every 45 minutes or every 60 minutes, you're able to understand the network impact of using that routing decision to find a solution on an input file and watching that solution propagate through the system. So you get to understand the impact of, for example, time that an order is waiting at a restaurant once it was assigned, right? So if you think about real-time meal delivery, you're making assignments of food to vehicles, and sometimes those assignments end up meaning that food is just sitting and getting cold waiting at the restaurant because you made the wrong decision and the driver is going to take forever to get there. So you get to understand those impacts that you can only understand when you're making real production decisions. And so if your switchback period is every 60 minutes, you would be able to see the impact, or even every 2 hours. 60 minutes sometimes is maybe not enough. Maybe you want to have like a wider time interval. And then you can see the impact on things like time waiting at the restaurant, driver acceptance rate, and so on. So yeah, I think like really you have to tune that time unit range based on the kind of problem and the nature of the routing problem.
Yeah, and something we didn't mention is those tests can actually run for quite a while sometimes. I've seen them run for like 6 weeks, for example, or 8 weeks. And it depends on the amount of time and the amount of data, observed data.
Right.
Okay, thank you very much. It was really interesting presentation about real world application. And I just take 1 more minute to share with you. Maybe it could be useful. Every time when we're talking about machine learning, and it was very active topic during these 3 days, people think about complex machine learning methods and neural networks. We do have customer a little bit similar to you. They do field service, but it's just different. But they're sending people to different locations, and they do have also constraints-based scheduler for these people. But one of the challenge for them is configuration. Who can do what, which area this driver can serve, etc. So what they do, they collect information about actual assignments did last time, and then they run rule engine as a machine learner, as a rule learner, and it defines parameters for next run of the actual scheduler. So maybe it could be simple. It's very, very simple, but it's extremely useful in production environment. So you may consider this. Anyway, thank you very much. It was a really good presentation. Thank you.
Thank you.
Okay. Good. So we will take a 5 minutes break, and our next presenter is Carolyn. Carolyn, can you show your screen?
Jacob,
Yes.
could you stop recording?
Oh yeah, thank you for reminding me.